Morning, everyone. Can you hear me? Okay. Yeah. As Amir said, I'm a fourth-year PhD student, and today I'll be talking about carbon in urban loan. As you might have seen in all over the news, we know that the global temperature is increasing, and what science have found is that there is a correlation between carbon dioxide emission and the global warming. And you can see that since 1876, we see that the temperature keeps to increase, and this happened to be when there is emission of carbon dioxide from many sources, such as in transportation, industrial, and other activities. And then on the right, we can see that what happens when we have greenhouse gases such as carbon dioxide. We can see that when they're emerge in the atmosphere, we can see that they can trap solar radiation, and then this is how we get this temperature to go up. So therefore, we need ways to address this. So likely, vegetation provide a natural way of removing carbon dioxide from the atmosphere, and then what is and might also have heard about carbon sequestration. So basically, what carbon sequestration is, it's simply just a process of removing carbon dioxide from atmosphere, and vegetation do this naturally. And you can know that urban lawn make a huge part of urban vegetation, where it's between 38 to 68%. But also, they play a role in capturing carbon, where they can capture between 254 to 2,000 kilogram of carbon per hectare per year. But what does this mean in the real world? So, in a study that was conducted, they found that 80 to 90% of the carbon captured in urban greeneries is captured by lawn. So you can see that lawn really plays a huge role in capturing carbon, especially in urban areas. Now we want to know, how does that happen? Through the process of photosynthesis, the lawn can capture carbon dioxide, and then they release water. You can see that this process needs water, where they exchange water to carbon dioxide. However, although the lawn can capture carbon dioxide, they also have a natural way of releasing carbon dioxide through respiration. We can see that when they capture carbon, they use it to produce sugar, and then through that metabolism, they also do roots can respire, and then they can emit carbon dioxide. But also, that's not only way that the lawn can release carbon dioxide back. It also comes from the microbial activities. So the roots, not only they do respire, but they also produce some byproducts, like a juice that normally is used by the microbes to, like, because they need those nutrients. And then through that process, the microbes can either feed on the dead roots or on that juice that is produced during the photosynthesis. And then they can also emit carbon dioxide. Then there is also the human aspect in emission. Mowing. We know that in mowing weeds, in some places they still use few powered mowers that can directly emit carbon dioxide. But in California, we know that there is a bill that has been passed to stop the selling of these mowers, and we hope that this is going to help. But we see that also mowing can be a huge contribution to the emission. And not only is just a emission from the mowing, but also the clippings that are produced, they can also enter the chain. So you can see that they can come back as fresh residues that the soil microbes are going to feed on. So you can see that this is a complete picture of how carbon dioxide is produced in urban world. It's captured and then produced again. Then the question is, how do we make sure that we are capturing more than we emit? And a little bit more about the carbon dynamics. We can see that this dynamics is also controlled by two factors: the natural emission. So we know soil moisture, it favors microbial activity. So when we have a moist soil, when the soil is not limited, so we see that the microbes are happy and they can uh, decompose all like dead roots and other plant biomass, and then that process can release carbon dioxide. But also temperature, the microbes need to work under favorable temperature. And then this brings to the role of irrigation in this cycle. So first, we know that urban landscape irrigation in general consists around 40 to 60% of urban residential water use. And then irrigation can improve carbon uptake through increasing the photosynthesis, and then hence that process we saw that it requires water. So when we irrigate, we're helping the plants to stay to capture carbon through that process because they have enough water to exchange in order to receive carbon dioxide. Also, we see that not only irrigation rate, but irrigation frequency can also promote carbon sequestration. We can see that on the left, deep and frequent irrigation can lead to a more developed root system. And as we see that the more developed root system, that's when carbon get moved down in the soil, and some of the when the microbes decompose the organic matter, then decompose roots and other plant residues, or get take on the other carbon released by the roots. They can be stored. Some of it is when the microbes do that, some of the carbon get over time, it gets stored, it get attached to soil particles, and then it stay in the soil. So we can see that the deeper the roots, the more carbon is going to be deeper in the soil. But compared to deep, infrequent, or shallow irrigation, we can see that the root system is different depending on how frequent you irrigate and how much you irrigate. However, again, since we have a huge, more developed root system, the respiration might be higher. So we can see that there is has to be like a balance in terms of how much you put down versus how much it goes back to the atmosphere. Therefore, what we're interested in is how does irrigation rate and frequency affect carbon efflux and the net carbon sequestration. So carbon efflux is just mean the emission, so via the root and microbial respiration. And net carbon sequestration is now what we really care much about, is how much is going to be left in the soil after accounting for all the emissions. So for the methods, we have a total of 36 plots for two Turfgrass species. But we choose to work on one block of the 12 plots with 12 treatments, just because of logistical purposes. But through this, for each Turfgrass species, we have 12 treatments, which includes different irrigation rate, which is how much we put, and then different irrigation frequency, which is how frequent we irrigate. And what we do, we measure soil moisture and temperature, because we saw that those are very important in terms of the carbon dioxide emission from the root and microbial respiration. And we also use a chamber to measure the emission from the Turfgrass. But we're also interested in the sequestration in general. So the way we measure sequestration, it's kind of like accounting. So we first collect samples at the beginning of the growing season, and then we'll also look at the end. And we look this in terms of biomass and soil. And then after that, we account for the hidden cost. So the hidden cost is other human-induced carbon emission. Like I mentioned, mowing is a huge part of that. But also, if you think about irrigation, when we irrigate, we're using electricity, and that electricity is produced somehow by emitting carbon dioxide. So we also account for that. It's not a huge part, but it also could be that. So we account for anything that we think could have contributed to that emission. And then at the end, we come up with what is the net carbon sequestered. So for some of the results, first this is results for the moisture. As we would expect, we see that there is increase in moisture as irrigation increase. This is because we're applying more water. So overall, we see that there is a increase in moisture as irrigation increase. But in terms of the frequency, we can see that there's a little bit when you look at buffalo grass, there's a little bit of higher moisture in 3-day versus 6-day. But in St. Augustine grass, we see a little bit in 6-day irrigation frequency compared to 3-day. But when you look at temperature, we see that temperature, it doesn't change that much. So you can see that it's pretty much like a straight line. If we were to draw a line that trend is, it's pretty much on the line. So, and when you look at this CO2 efflux, which is the emission, we see that again, we see increasing trend. And we can guess why. First, there is the moisture that is going up, that we found that it's impacting this the microbial activities. But also one other hypothesis is the roots. The plants are bigger. There is huge biomass when we irrigate. So that's why we could see an increase in the emission, which is this is not from the natural process of microbial and root activities. Yeah, and another thing that we noticed was that in buffalo grass, we found that the emission was higher in 3-day, in the less frequent, compared to 6-day per week. But in St. Augustine grass, it was the different. And but it's not huge. It was for some certain growing season was higher and other growing season was not. The difference was not significant. But what that tells us is that it could be a little bit what driving the emission in these two turfgrass species might be a little bit different. But overall, we see a consistent trend in the irrigation. Now we combined all the data for the two turfgrass species for just this simplicity for this presentation to see what's really driving emission. And the graph on the left, it's showing what we call the percent of response variance. So it's kind of telling us how important is this variable to the emission. And what we found when we combine the data for the two species is that the soil moisture is the main driving factor, the emission. And then we see that the soil temperature is doesn't have much impact. And we've seen that in the results that the trend was kind of flat. But one thing that is interesting, the NDVI, it's a measure, it's kind of a vegetation index that correlates with the plant health. It can tell us much about the vegetation cover, which also correlates with the vegetation biomass. So, and this one, we include this to kind of tell us how does the plant health or the plant biomass correlates to the emission. And we can see that the NDVI is the second in terms of contributing to the important to the emission. So what this tells us is that when the plant is healthy and it's made bigger, the biomass is higher, then we might see higher emission just because that means if it's healthy, it has good roots, and then they contribute to respiration. And then you can see that we have a really strong correlation between soil moisture and the emission. And then to kind of understand, since this is a little bit of complex, we apply water, and then how does water leads to temperature and the plant growth. So we used a path analysis, which is a method of trying to understand a complex system where different paths are impacting each other. And then what we were able to find was that overall in the two species, we see that irrigation rate, as you can see where you see a star, is where the impact is significant. And where there is not a star, it means that it's not statistically significant. It doesn't mean that it's not there, it's just not statistically significant. And then what we see is that overall irrigation rate is statistically significant in terms of impacting the soil moisture. And then we see that the moisture, as the major driver that we saw, has direct impact on the CO2 efflux. And then why we think this? It's because we know that the microbes respond to the moisture directly. However, the moisture also can affect the plant growth, that we know that the plant growth can also affect the CO2 efflux. So we can see that it has both direct and indirect impact. And then the soil temperature, the moisture can a little bit fluctuate the soil temperature, but soil temperature also has can have an impact on CO2 efflux. So we kind of had this kind of schematic to look at how does irrigation affect the CO2 efflux. We see that the impact is indirectly through changing the moisture. Then now, what about carbon sequestration? We haven't analyzed samples for the two species, but I did a little bit of preliminary analysis in buffalo grass. I was just curious to see comparing the highest irrigation to the lowest irrigation, and then also the two irrigation frequencies. And what I found is that in 80%, which is our highest irrigation rate, we see the higher carbon sequestered in the soil. And compared to and then these are the two highest irrigation rate. And then you see that compared to this 30%, which is the lowest irrigation rate. However, one thing that you can also find is that less frequent irrigation has the higher carbon compared to more frequent irrigation, or we can call this non-restricted irrigation compared to that. And this matched the initial hypothesis that we saw, that because of the way frequency affected root distribution, and root plays a paramount role in terms of carbon sequestration, but also distribution. And then we can see that in the future, I'll probably talk about that in the next slides, but we want to understand why, and then hypothesis again is the roots. But we can see that, yeah, that the result shows that the less frequent irrigation leads to higher carbon sequestration. As a summary, overall, we see that the CO2 efflux increases as irrigation increases. However, the sequestration also increases as the irrigation increases. And we can see that the less frequent deep irrigation promotes more carbon storage. So basically, we can see a little bit of, we see higher emission, but also we see more capturing. Then the next step, what we really want to do is measure the carbon sequestered in both soil and plant biomass. And then we also want to account for hidden carbon cost, and then do the accounting that I mentioned earlier to look at then how did the overall irrigation affect the net carbon sequestration. As you can see the figure on the right, this is a study that was done, and you can see that on the below zero is the net carbon sequestered, it's the carbon sequestered in the soil. They measure the carbon captured by the plant. And then on the above zero, it's the emission. Then you can see that this emission is coming from management practices, such as irrigation, fertilizer, and mowing. So you can see that in irrigated lawn, they're comparing urban irrigated and non-irrigated. We can see that when there is irrigation, plants grow fast, and then they need, and biomass, they need more fertilizer, and then also need, of course, mowing. Then we can see that the emission is higher, but in non-irrigated, they probably don't do any mowing or other management. They just slowly. So we can see that we see higher carbon capture, but again, when you look at the emission, we see that it's higher. So it's a matter of knowing that we're carbon neutral, or at least we're sequestering more than we emit. Yeah, but overall, we see that the turfgrass can capture carbon, but we have to also account for other emissions to make sure that we are capturing more than we're emitting. And we see that irrigation can play a paramount role in this process. That's the end of the presentation, and I'm ready for any question that you might have. Thank you.
Yeah, thanks, Jean-Claude. Actually, you got a couple questions, and I think we got a little bit of time right now. The first one, many xeriscape landscapes use mostly stones and rocks with little plant life. Is this less beneficial than lawns in regard to carbon absorption?
Yes, we haven't analyzed in the other landscape plants to see their carbon, but based on just the data I've seen, yeah, like it's in terms of sequestration, it's less beneficial. But one could argue that because they probably not doing the mowing or anything, so they're probably not emitting a lot, but also they're not capturing a lot. So it's going to be a matter of doing the balance and looking at you're not capturing any, or maybe you're capturing a little bit of carbon, but you're also not emitting any carbon. But in the loan, depending on how someone managed the loan, if it's highly managed, sometimes you end up emitting more than you captured. So I would say that overall, like if you're just looking at the capturing carbon, not having vegetation it's not beneficial in terms of carbon capture. But in terms of the budget, that's where it's very depend on the management practices, and it differs depending on how many times someone mow. If you mow 7 times a day versus someone who mows once a week, that plays a difference.
Yeah, thank you for that. Another question I had, isn't fescue the more common type of grass used in Southern California? Any data related to this kind?
Well, I don't have any data in terms of which species in Southern California. I don't know if Amiri has any insight on that.
So one way that you can answer this is that why did you decide, or we decided to work on warm season turfgrass species as opposed to cool season species from the water use standpoint?
Yeah, so we decided to work on the warm season specifically because they are more drought tolerant, because of their physiological features. So that's why we mostly focus on the warm season, and the research focus on, because we think that this is going to be the future in this region based on the water issue. So that's why we are mostly focusing on these warm season turfgrass species.
So Jean-Claude, I know I asked you to focus on carbon, but off the top of your head, do you remember how much water, based on your research, we should apply to each of these species to keep them at the minimum level in terms of aesthetic values?
Yes, in terms of irrigation rate, I'm not sure how the